Hi, this is question 5, multiple choice question, and I'm going to go through the answer, but in the meantime I'm going to just have a look in detail at phosphoric acid. So you can see there's 3 hydrogens per phosphate ion. Right, so this is probably a new type of acid. You're very familiar with hydrochloric acid, where you have 1 hydrogen per acid molecule. And you're also familiar with sulfuric acid, H2SO4, where you have 2 hydrogens per acid molecule. But here in phosphoric acid, we have 3 hydrogens per acid molecule. Okay, and how that looks like, if I was to draw the displayed formula of phosphoric acid, would be, let's have a look at the phosphate ion. We've got phosphorus in the middle, and we've got a double bond to an oxygen, and we've got 3 other oxygens, but these 3 oxygens are bonded to hydrogens. Right, and so these 3 hydrogens are the acidic hydrogens. So this you can see is H3PO4. So when this acid molecule H3PO4 dissolves in water, what happens is that the electrons that are in the oxygen-hydrogen covalent bond stay with oxygen, H1. So we represent that movement of electrons by these curly arrows, which we'll come to many times in your A-level chemistry course. So what that then leads on to is an anion that looks like this. You've still got your phosphorus atom with a double bond oxygen, but now this oxygen has got a minus charge because it's got that extra electron that used to be hydrogens, as do the other 2 oxygens. Okay, so we draw it's an ion, so we draw it in square brackets, and instead of actually putting the 3 negatives here, sometimes we put them top right hand corner of the square brackets like so, and then when that becomes sodium phosphate, like I've underlined here, the compound of course has to be neutral, right? And this anion has got 3 minus charges, so we need 3 sodium ions, because each sodium ion is 1 plus ion, so you need 3 sodium ions to neutralize the 3 minus charge on the 1 phosphate ion. So that's why the salt has the formula Na3PO4 like so. These are actually, all these ions are dissolved in water, so swim around independently, but that's the ratio that they're in aqueous solution. Okay, so that said, let's actually go back to the question, answer that. Right, so which statement is correct about this reaction? It's a neutralization reaction. We've got phosphoric acid reacting with sodium hydroxide, making sodium phosphate and water. So usual acid plus alkali goes to salt plus water reaction. But the interesting thing here is that we've got a 1:3 ratio of the acid and the alkali, because of course our hydroxide ion is a 1 minus ion, and that's going to react with the hydrogen ion from phosphate. So these 2 are going to react and going to make a water molecule like so. But because we've got 3 hydrogen ions coming from each acid molecule, you're going to need 3 hydroxide ions to get full neutralization. Okay, so that's the important thing about this question, is to notice the 1:3 ratio. Then of course you could say 1 mole of phosphoric acid reacts with 3 moles of sodium hydroxide in that ratio. Here you could actually work out the moles using the volume and the concentration of phosphoric acid, so that would give you moles of phosphoric acid, and that would equal 3, you would need 3 moles of sodium hydroxide. Okay, so you could do that little multiplication there, convert it to decimeters cubed if you want, and then use this concentration here if you needed to calculate the volume of sodium hydroxide that we need to provide 3 times the moles of it compared to phosphoric acid. Or there's a quick way of doing it and noticing that there is a 1 to 3 ratio between 0.2 and 0.6, and so the volume is just going to be 25, like so. So either calculate it out in full or notice the 1 to 3 ratio in the concentrations. Either way, you get the answer A. So that's your correct answer. Okay, here's another multiple choice question I'm going to help with. You might recognize it as question 8 in homework. And it looks like we're mixing up 2 acids. Okay, we've got some hydrochloric acid and we've got some nitric acid. Notice that they are both what you call monoprotic acids. There is 1 hydrogen per acid molecule in both cases. Okay, and we're given a volume and a concentration, so we can work out the number of moles of the acid molecules in both cases because we've got the volume and the concentration of both. Okay, so here let's just step back a little bit and think about moles of hydrogen ions, right, compared to versus moles of acid molecules. That's what we're going to think about just now. So in an acid like hydrochloric acid, hydrogen chloride is a gas, right? So you've got a hydrogen atom covalently bonded to a chlorine atom, and when you dissolve that in water, what happens is this bond dissociates, right? So the 2 electrons in it stay with the chloride, and you get a hydrogen ion because it doesn't have its electron anymore, and you get a chloride ion, aqueous. That's what happens when it dissolves. Right, so I'm just going to put plus aqueous here, and that was a gas as hydrogen chloride. So that is what happens when you dissolve hydrochloric acid. So now the thing is that when you look at this molecule, for every acid molecule, which is, let's just change colour, right? So the acid molecule is the hydrogen chloride. For every one of those molecules, we have 1 hydrogen ion that's been created here. Okay, so that's a 1-to-1 ratio in hydrogen chloride. If we were to look at nitric acid, that's HNO3. In fact, why don't I just draw it out fully? So we've got a nitrogen with 2 oxygens double bonded and an oxygen with a hydrogen on it. And so when this molecule here, this is the nitric acid molecule, when that dissolves in water, you're going to get this bond dissociating and both electrons staying with the oxygen. All right, so that process is going to create a hydrogen ion because it's lost its electron, and a nitrate ion. This extra electron here is hydrogen's old electron. Okay, so again in this case you can see that the nitric acid molecule, for every one of those molecules we also have 1 hydrogen ion, and so that's a 1-to-1 ratio. And let's just look at a third example. All right, so let's have a look at sulfuric acid. I'll draw sulfuric acid out in full. So you've got like this. This is H2SO4. Right, and in the same way, this hydrogen, in the same way, when it dissolves in water, the electrons that are in that covalent bond stay with the oxygen, and the electrons that are in this covalent bond stay with that oxygen. And so this is what you get. You get 2 hydrogen ions, and you get a sulfate ion, like so. Right, so in this case, for every one sulfuric acid molecule, we have 2 hydrogen ions. Okay, so that means that the concentration of hydrogen ions, which we can express like this, equals 2 times the concentration of sulfuric acid, like so. Okay, so that's a slightly trickier case. If one of our acids was sulfuric acid, the question would be slightly trickier. But as it happens, just going back to the question, we've got hydrochloric acid, monoprotic, and we've got nitric acid, monoprotic. All right, so the question is, what is the hydrogen ion concentration in the resulting solution after we've added these 2 acids together? So we have to work out the moles of hydrogen ions, and we'll write that like this. So this is going to be, let's write it out like this. So the moles of hydrogen ions, so let's say moles of hydrogen ions, let's call that resulting, like so. It's going to be the moles of hydrogen ions that came from the HCl plus the moles of hydrogen ions that came from the nitric acid, like that. Okay, so this one we can calculate with our usual equation, concentration times volume. All right, so this is going to be concentration is 6 moles per dm cubed. Times our volume is 50 over 1,000, and we can see that that equals, all right, 6 5 is 30, 300, so that's 0.3. We've got 0.3 moles of hydrogen ions from the hydrochloric acid, and we do the same sort of calculation for our nitric acid. We've got concentration of 3 times volume of 90 in dm cubed, like so. And so that equals 3, that's 270 divided by 1,000 is 0.27. Okay, so we're going to add these 2 together, so that's 0.57. So we've got moles of hydrogen ions resulting is 0.57 moles. Okay, so but the question is asking us for concentration, you see, so we have to turn that into concentration. So we know that concentration equals moles over volume. Volume, moles we just worked out. Volume is our 50 plus our 90. Okay, so which is 140. All right, so our concentration is going to be our 0.57 moles divided by 140 in dm cubed, like so, and that turns out to be 4.07, which we're going to round to 4.1, which is answer C. And so there you have it, plus a little, I don't know if it's a reminder or for the first time, a comparison of moles of hydrogen ions per mole of different acid molecules. Hi, next question that people struggle with in this acids homework is this one. And this is quite tricky right enough. So what I would recommend is I'd recommend a strategy called storyboarding. I'll demonstrate it now. So pause the video now and just read through the question, and then start it again when you've got an idea of what the question is on about. Okay, so now I'm going to storyboard it. So this question here describes what you did in the practical in class, where you actually had some sodium sulfate, I think it was, and you made up a standard solution of it. Okay, so when we made up the standard solution, we took a beaker and we put the solid in the beaker, didn't we? Right. So, but in this case, we've got 2.24 grams of acid A. All right. Let's call our acid A H, because we need a H in the acid. We're going to call it HX, right? Because it reacts in a 1-to-1 ratio. Anyway, we're going to call it HX. and it's 2.24 grams we've put in our beaker, right? And then we add some water to it to dissolve it, stir it around a bit, and then we're going to add this to a volumetric flask, aren't we? Okay, so let's draw our volumetric flask very roughly, like so. All right, and that makes up this amount of solution, but our graduation mark is there, right? So we're going to make it up with water to our graduation mark. So now we've got 250 cm cubed of solution that contains our 2.24 grams of our acid. Okay, so then you're going to use a pipette. All right, so let's just draw a little pipette, like so. You're going to use a pipette, and you're going to take, with that pipette, you're going to take 25 cm cubed, right, and you're going to put it into a conical flask. All right, so let's draw our conical flask like that, and you put your 25 in there. All right, so this is now 25 cm cubed of that solution, so it's the same concentration of that solution. And then you've got a burette here, and in that burette you have your sodium hydroxide. All right, so you fill it up with sodium hydroxide, right, and you know your concentration is your 0.12 mole per dm cubed. And right, you do your titration, and there it is, and you're told that your tetra is 25.25. All right, so we can call that volume is 25.25 cm cubed there. So that's a storyboarding of our practical that we did, and as is similarly described in this question here. So now we have to answer the question. All right, so let's start off with the reaction that goes on in this conical flask. So we've got our acid, which we've called HX. We've got our alkali, which is sodium hydroxide. So we're going to make a salt, right, which in this case is NaX, and water, of course, right? And we're told that it's a 1-to-1 ratio, right? So that's nicely balanced now already. So what we might want to do the first time is work out how many moles of sodium hydroxide we used in the neutralization of our acid. Okay, so moles is concentration times volume, so we've got 0.12 times our 25.25 in dm cubed. All right, and so that is 3.03 times 10 to the minus 3. Just done that quickly, hopefully it's right. Mole per dm cubed. So that's our number of moles of sodium hydroxide that were required to neutralize 25 cm cubed of our acid. Okay, so given that we've got this 1-to-1 ratio, and we have 3.03 times 10 to the minus 3 moles of our sodium hydroxide, we must have 3.03 times 10 to the minus 3 moles of our acid in the conical flask here. Okay, but of course this was only an aliquot, wasn't it? Right, to get the number of moles that were in our volumetric flask, we have to multiply it up by 10. The 10 comes from 250 over 25. Okay, so now we can say here our moles of HX in 250 equals I'll write this out fully, 3.03 times 10 to the minus 3 times 10, all right, which equals 3.03 times 10 to the minus 2. Okay, so now that number there, 3.03 times 10 to the minus 2, is the moles that will, of HX that were in our volumetric flask, which is the same as the moles that were in our solid. All right, so this corresponds to 2.24 grams. So now you notice that we have both, we've got both moles and grams. And you remember the standard equation, moles equals mass over mR, right? So mR equals mass over moles. Right, in this case, mass is our 2.24. Our moles is 3.03 times 10 to the minus 2. And so do that little sum and you get 73.9, which is our MR of our acid. Hopefully that's helped.